What is light actually made of when we look beyond waves and particles and listen to what quantum field theory quietly says about the fabric of reality itself? If you enjoy these calm explorations of physics and the universe, you are always welcome to like or subscribe, and if it feels natural, you can share where in the world you are listening from tonight, simply as a gentle point of connection, and then we can let the science unfold at its own unhurried pace. Light is so familiar that it almost disappears from our curiosity. It fills rooms, bounces off walls, slips through windows, and carries the colors of the world into our eyes. Yet, when physicists ask what light is made of, the answer is not a substance in the ordinary sense, not tiny glowing grains moving through empty space, and not merely ripples in an invisible medium. In quantum field theory, light is understood as an expression of something deeper, something that exists everywhere, even in perfect darkness. It is an activity of a field, a quiet but ever-present structure that underlies space itself. To approach this idea gently, it helps to step back from everyday language. In classical physics, light was described as an electromagnetic wave, an oscillation of electric and magnetic fields spreading smoothly through space. This picture works beautifully for explaining reflection, refraction, interference, and the elegant patterns of diffraction. James Clerk Maxwell's equations captured this wave nature with extraordinary precision, predicting that light travels at a fixed speed, and that electric and magnetic phenomena are woven together into a single dynamic system. For many years, this seemed like the final word. Then, in the early 20th century, experiments began to whisper that something was missing. When light struck metal surfaces in the photoelectric effect, electrons were ejected in a way that could not be explained by waves alone. The energy transfer behaved as if light arrived in discrete packets. Albert Einstein proposed that light sometimes behaves as if it is made of quanta, later called photons, each carrying a specific amount of energy related to its frequency. This idea was unsettling, not because it was complicated, but because it challenged the smooth continuity that physics had come to rely on. For a while, light lived a double life. In some experiments, it behaved like a wave, spread out and interfering with itself. In others, it behaved like a particle, arriving in localized clicks on a detector. This wave-particle duality was not a satisfying explanation so much as a careful truce. It worked, but it left a lingering question hanging in the background. What is light really underneath these different behaviors? Quantum field theory emerged as a deeper framework, not just for light, but for all known particles. Instead of treating particles as tiny objects moving through space, quantum field theory begins with fields. A field is something that has a value at every point in space and time. Temperature in a room is a simple example, varying from place to place. In physics, fields are more abstract but more fundamental. According to this view, the universe is not made primarily of particles, but of fields that fill all of space. In quantum field theory, there is an electromagnetic field that exists everywhere, even in regions where no light is shining. This field is not something added on top of space. It is part of the basic description of reality. Light, in this framework, is what happens when the electromagnetic field is excited in a particular way. A photon is not a little bead of energy traveling through emptiness. It is a discrete excitation, a tiny ripple of activity in the electromagnetic field itself. This is a subtle shift, but a profound one. Instead of asking what photons are made of, Quantum field theory invites us to see photons as events rather than objects. They are localized disturbances, momentary expressions of the field's underlying structure. When the field is calm, we call it vacuum. When it vibrates in just the right quantized way, we observe light. The vacuum, in this sense, is not nothing. It is the lowest energy state of all the fields that exist. Even when no photons are present, the electromagnetic field still exists, quietly fluctuating due to the uncertainty principles of quantum mechanics. These vacuum fluctuations are not just mathematical curiosities. They have measurable consequences, such as the Casimir effect, where two uncharged metal plates placed very close together experience a tiny attractive force due to changes in the allowed field fluctuations between them. So, when quantum field theory speaks of light, it is really speaking about changes in the state of the electromagnetic field. A photon corresponds to the smallest possible change, the smallest packet of excitation that the theory allows. This is what gives light its granular character in certain experiments. The granularity is not because the field is made of particles, but because its excitations come in quantized amounts. This idea can feel abstract, so it helps to rest with a softer analogy. Imagine the surface of a perfectly calm ocean stretching endlessly in all directions. The water itself is always there, even when the surface is smooth. A wave traveling across the surface is not a separate thing made of new water. It is a pattern of motion, a coordinated rise and fall of what was already present. In quantum field theory, the electromagnetic field is like the ocean, and photons are like the smallest possible ripples that can move across it. But even this analogy only goes so far, because quantum fields are not made of any familiar substance. They are mathematical entities that assign values and operators to every point in space-time. Their behavior is governed by equations that encode symmetries, conservation laws, and probabilities. What feels remarkable is that these abstract structures correspond so precisely to what we measure in experiments, from the glow of a candle to the light from distant galaxies. The electromagnetic field is special in another way. It is associated with a fundamental symmetry known as gauge symmetry. This symmetry is not about space or time, but about how certain mathematical descriptions can change without altering physical predictions. From this symmetry emerges the existence of photons themselves. In a very real sense, light exists because the laws of physics allow a certain kind of freedom in how we describe electric and magnetic potentials. Within quantum field theory, every type of particle corresponds to a field. Electrons are excitations of the electron field. Quarks are excitations of quark fields. Photons are excitations of the electromagnetic field. The distinction between matter and force becomes less rigid. What we call forces are mediated by fields whose excitations we observe as particles. Light is the messenger of the electromagnetic interaction, but it is also a physical phenomenon in its own right, capable of carrying energy, momentum, and information across vast distances. When a charged particle like an electron accelerates, it disturbs the electromagnetic field around it. That disturbance propagates outward at the speed of light. In quantum field language, the electron interacts with the electromagnetic field, and photons are emitted. The field responds according to its equations of motion, and the result is what we observe as radiation. Nothing material is thrown off the electron. The field simply rearranges itself. This way of thinking gently dissolves the question of what light is made of, because it suggests that light is not made of parts in the usual sense. It is made of the field being itself, but not in its quietest state. It is the field expressing a little more energy here, a little less there, in patterns that move through space-time. Quantum field theory also explains why light always travels at the same speed in a vacuum. The speed of light is not a property of photons as objects, but a property of the electromagnetic field and its relationship to space and time. This relationship is woven into the structure of space-time itself, as described by special relativity. The field's equations allow disturbances to propagate only at this invariant speed. Light does not choose to move this way. It cannot do otherwise. Another quiet insight of quantum field theory is that photons are massless. This does not mean they are insubstantial or unreal. It means that the electromagnetic field has no rest mass term in its equations. As a result, its excitations always move at the speed of light and cannot be brought to rest. This is why you cannot sit alongside a photon or hold one still. It is always an expression of motion, always a process rather than a thing. Despite being massless, photons carry momentum. When light reflects off a mirror, it exerts pressure. This radiation pressure has been measured and even harnessed in ideas like solar sails, where spacecraft could be gently pushed by sunlight. In quantum field theory, this momentum arises naturally from the way the electromagnetic field's energy and stress are distributed through space. At very low intensities, light reveals its quantum nature in a particularly intimate way. In experiments where photons are sent one at a time through a double-slit apparatus, each photon arrives at a detector as a single localized event. Yet over time, an interference pattern emerges, as if each photon had somehow explored all possible paths. In quantum field terms, the electromagnetic field evolves according to wave-like equations, even when its excitations are detected discretely. The field spreads out. The detection is local. This is one of the moments where quantum field theory feels less like an answer and more like a deepening of the mystery. It provides a consistent mathematical framework, but it does not give us a simple picture that fits comfortably into everyday intuition. Instead, it invites a quieter kind of understanding, one that accepts that reality at its core may not be built from little objects moving around, but from relationships, symmetries, and fields that do not resemble anything we encounter directly. The idea that light is an excitation of a field also helps explain why empty space is not truly empty. Even in the absence of photons, the electromagnetic field has a ground state energy. Other fields do too. The combined effect of all these fields gives the vacuum a subtle structure. Particles can appear and disappear briefly as fluctuations, borrowing energy in ways allowed by quantum uncertainty. These virtual processes influence measurable quantities, such as the precise magnetic moment of the electron, calculated and measured to astonishing accuracy. From this perspective, light emerging from a star or a lamp is not created from nothing. It is a rearrangement of the electromagnetic field's energy, guided by interactions with charged matter. Atoms transition between energy levels, and the field responds by producing photons with specific frequencies. The color of light corresponds to how the field is excited, to the rhythm of its oscillation. Quantum field theory also clarifies why photons do not interact strongly with each other under ordinary conditions. The electromagnetic field is linear to a very good approximation, meaning that its excitations pass through one another without direct interaction. Two beams of light can cross paths and continue on unchanged. At extremely high energies, subtle nonlinear effects appear, predicted by quantum electrodynamics, the quantum field theory of light and charged particles. These effects have been observed indirectly and confirm the depth of the theory, even as they remain far removed from everyday experience. What feels especially gentle about this understanding is that it removes any sharp boundary between light and the rest of the universe. Light is not a visitor traveling through space from distant places. It is space itself, or rather the fields that inhabit space, doing something dynamic. When you look at a star, you are not receiving tiny objects that left its surface long ago. You are participating in a process that links the star's charged particles, the electromagnetic field across the cosmos, and the sensitive chemistry of your eyes into a single, continuous physical story. Historically, quantum field theory was developed through the work of many physicists, including Paul Dirac, Richard Feynman, Julian Schwinger, and Shinichiro Tominaga. Their insights showed how to combine quantum mechanics with special relativity in a consistent way. For light, this combination is essential because photons are inherently relativistic. The success of quantum electrodynamics, the specific quantum field theory describing light and charged particles, is often cited as one of the most accurate theories ever constructed, with predictions matching experiments to many decimal places. Yet, despite this precision, the theory remains conceptually subtle. It does not answer questions in the way a story does, with clear beginnings and endings. Instead, it offers a framework in which questions dissolve into structures. What is light made of becomes less about composition and more about behavior. Light is what the electromagnetic field does when it is not in its quietest state. There is a certain calm that comes from this view. The universe is not a collection of disconnected things, but a set of fields continuously present, continuously capable of expression. Light is one such expression, endlessly varied, carrying energy from place to place, shaping chemistry, biology, and perception, all while being rooted in a single underlying field that permeates everything. Even darkness, in this sense, is not the absence of the field. It is the absence of certain excitations. The field remains, waiting, capable of responding whenever conditions allow. This is why the language of quantum field theory often feels more like music than machinery. Fields have modes, frequencies, ground states, and excitations. Light is a note played on the electromagnetic field, sometimes soft, sometimes intense, always consistent with the deep symmetries that govern its existence. As this understanding settles, it becomes possible to see light not as something separate from matter, but as part of the same underlying tapestry. Matter itself is made of fields, interacting with one another, exchanging energy through photons and other quanta. The distinction between substance and interaction blurs. What remains is a universe described by fields and the patterns they form. And so, according to quantum field theory, light is not made of smaller pieces in the way a wall is made of bricks. It is made of the electromagnetic field being gently excited, one quantum at a time, across the vast and quiet stage of space-time, a Asai stage that is never empty, never truly still, and always ready to glow. That idea that the vacuum itself is alive with structure carries a quiet sense of fascination, not the loud kind that demands attention, but the kind that gently widens the mind. In quantum field theory, empty space is not an empty container waiting to be filled. It is already full of fields, already active at a level beneath direct perception. Light does not enter space as a visitor. It emerges from what is already there. When physicists calculate how light behaves, they do not track tiny particles hopping from point to point. They describe how the electromagnetic field changes, how its possible states evolve over time. These states are quantized, meaning the field can only change in certain allowed steps. Each of those steps corresponds to a photon. This is not an added rule imposed by hand. It falls naturally out of the mathematics when quantum principles are applied to a field that respects the symmetries of space and time. There is a subtle elegance here, and it carries a feeling of genuine wonder. The same framework that explains why atoms emit light at specific colors also explains why radio waves stretch across continents, why X-rays pass through flesh but not bone, and why gamma rays emerge from the most violent events in the universe. All of these are the electromagnetic field, excited in different ways, vibrating at different frequencies, yet governed by the same underlying structure. In quantum field theory, frequency is not just a descriptive label. It determines the energy of a photon. Higher frequency means higher energy, not because the photon is somehow heavier or faster, but because the field is oscillating more rapidly. This relationship is exact and universal. It links the deep mathematics of the theory to the colors we see and the technologies we build. There is a quiet delight in realizing that the blue of the sky and the operation of a laser are expressions of the same rule. One of the most striking consequences of this view is how it reframes the idea of interaction. When two charged particles influence each other, they do not reach across empty space and pull or push directly. Instead, they interact through the electromagnetic field. In quantum field language, they exchange photons. These photons are not always real, detectable particles. Often, they are virtual excitations, temporary disturbances in the field that exist only within the limits allowed by quantum uncertainty. This is one of those moments that carries a soft thrill of insight, because it shows how forces themselves arise from field activity. These virtual photons are not objects flying back and forth in the usual sense. They are bookkeeping elements in the theory, reflecting how the field responds to charges. Yet their effects are measurable. They shape the structure of atoms, determine the stiffness of materials, and govern the chemistry that makes life possible. Light, in its visible form, is only a small part of this broader electromagnetic conversation happening everywhere, all the time. Another gently astonishing aspect of quantum field theory is how it treats creation and annihilation. In everyday language, creating light sounds like making something from nothing. In the field picture, nothing so dramatic happens. Energy is transferred from one part of the system to another. An excited atom loses energy. The electromagnetic field gains an excitation. A photon appears. Later, that excitation may be absorbed by another atom, and the field returns to a quieter state. The total accounting remains balanced. What changes is how the energy is distributed among fields. This way of thinking dissolves the sharp edges of cause and effect. Light emission is not a sudden event localized at a point. It is a smooth process in which the combined system of matter and field evolves according to precise rules. The photon is simply how that evolution is registered when the field's excitation becomes distinct enough to travel and be absorbed elsewhere. There is a calm satisfaction in knowing that this picture is not philosophical speculation. It has been tested again and again. Quantum electrodynamics predicts tiny corrections to the energy levels of hydrogen, known as the Lamb shift, and those predictions match experiments with remarkable accuracy. It predicts how light bends around charged particles, how it scatters, how it polarizes. Each success reinforces the idea that light, at its core, is field behavior made visible. The polarization of light offers another window into this structure. Polarization describes the orientation of the electromagnetic field's oscillations. In quantum terms, it reflects different states of the photon, different ways the field can be excited. When light passes through a polarizing filter, it is not being mechanically altered. Certain field excitations are allowed through, while others are absorbed. This, too, feels quietly beautiful, because it shows how deeply the field description penetrates even the simplest optical effects. Quantum field theory also explains why light has no charge. The electromagnetic field interacts with charged fields, but it does not carry charge itself. This neutrality is built into the symmetry of the theory. As a result, photons can travel vast distances without being deflected by electric fields, making them excellent messengers across the universe. There is a gentle awe in realizing that the light from distant galaxies has crossed billions of years of space, guided only by the structure of the field and the geometry of space-time. When gravity enters the picture, the story becomes even richer. According to general relativity, space-time itself can curve, and light follows that curvature. In quantum field terms, the electromagnetic field lives on a dynamic space-time background. Its excitations trace paths shaped by gravity. This is why light bends around massive objects, and why we observe gravitational lensing. The field does not resist or ignore gravity. It responds naturally, its behavior inseparable from the structure of the universe it inhabits. There is a sense of quiet amazement in how seamlessly these ideas connect. Fields, space-time, energy, and interaction are not separate chapters. They are facets of a single description. Light sits at the intersection of them all, revealing the geometry of the cosmos while being governed by quantum rules that operate at the smallest scales. Even the act of seeing becomes more intimate through this lens. When light enters the eye, photons are absorbed by molecules in the retina. Those absorptions trigger chemical changes, which lead to electrical signals, which the brain interprets as color and brightness. At no point does the photon remain intact as an object. It is an exchange of energy between fields, cascading through different layers of physical description. There is a soft sense of connection here, a realization that perception itself is a dialogue between fields. Quantum field theory does not strip light of its mystery. It relocates that mystery. Instead of asking how something travels through nothing, it invites us to see that there is no true nothingness. There are fields everywhere, quietly structured, ready to be excited. Light is one of the most graceful ways those fields reveal themselves, carrying information without carrying substance, shaping the universe while being woven into its deepest fabric. And the fascination grows not because the answers are final, but because they are coherent. They fit together. Light, according to quantum field theory, is not an object drifting through emptiness. It is the electromagnetic field, briefly stirred, moving through space-time in patterns that are as precise as mathematics and as gentle as illumination itself. That coherence, the way the pieces settle together without friction, carries a quiet sense of fascination. It suggests that light is not an exception in nature, not a special substance set apart, but a clear example of how reality behaves when described at its most fundamental level. One of the deeper insights of quantum field theory is that fields are not passive backgrounds, they are active participants. The electromagnetic field does not merely allow light to exist, it defines what light can be. Its structure determines the possible energies of photons, their polarizations, their interactions, and even their absence. When physicists say that a photon is a quantum of the electromagnetic field, they are saying that light is the field revealing one of its simplest, indivisible expressions. This becomes especially striking when we consider how universal this picture is. The same electromagnetic field exists everywhere, from the space between galaxies to the space between atoms in your body. There are not separate fields for different regions. There is one continuous entity, stretching without seams. When light travels, nothing migrates from one place to another in the ordinary sense. The field's excitation shifts, propagates, and reshapes itself across space and time. There is a gentle sense of awe in realizing that when a photon leaves a distant star, it is not carrying a piece of that star with it. It carries no material fragment, no imprint of substance. It carries energy and momentum, encoded in the state of the field. What arrives here is not a traveler from far away, but a local manifestation of the same field, shaped by events that occurred long ago and far away. Quantum field theory also reframes the idea of individuality. Photons are often described as identical, and in this framework, that statement becomes almost inevitable. All photons are excitations of the same field. There is no label or internal structure that distinguishes one photon from another. Their identity lies entirely in their state, their energy, direction, and polarization. This indistinguishability is not a limitation of measurement. It is a reflection of how deeply unified the field description is. This has subtle but profound consequences. It explains why photons obey specific statistical rules, why they can pile into the same state in lasers, producing coherent beams of light. In a laser, many photons occupy the same quantum state of the electromagnetic field, oscillating in lockstep. This coherence is not imposed from outside. It arises naturally from the field's quantum nature and the way it interacts with matter. There is a soft excitement in recognizing that coherence, something that feels almost poetic, has such precise physical meaning. Coherent light is not just orderly. It is a collective behavior of the field, a synchronized expression that amplifies itself through interaction with atoms, designed to encourage that synchronization. The quantum field picture also clarifies why light can be both spread out and localized. Before detection, an excitation of the field can be described as extending over a region of space, evolving according to wave equations. When light is detected, the interaction with matter localizes that excitation. Energy is transferred at a specific place and time. The field changes state accordingly. There is no contradiction here, only a shift in how the field is configured. This shift depends on interaction. Light does not collapse or choose in isolation. It responds to the systems it encounters. Detectors, atoms, and molecules are themselves fields in excited states, and their interactions with the electromagnetic field determine what is observed. This relational aspect carries a quiet sense of fascination, because it suggests that observation is not a passive act. It is a physical process woven into the same field-based description as everything else. At extremely high energies, the electromagnetic field reveals even more of its depth. Quantum electrodynamics predicts that photons can briefly transform into pairs of charged particles, and then back again, as long as the rules of energy and uncertainty are respected. These processes happen fleetingly, but their cumulative effects are real and measurable. Light, in this sense, is never entirely separate from matter. The fields are coupled, capable of transforming into one another under the right conditions. This coupling is governed by constants that appear simple but encode profound structure. The fine structure constant, for example, determines the strength of the electromagnetic interaction. Its value influences how strongly light interacts with charged particles, shaping the size of atoms, the spectra of elements, and the chemistry of life. There is a quiet reverence in seeing how a single number, emerging from field theory, can ripple outward into the complexity of the world. Quantum field theory also sheds light on why the speed of light is a limit, not just for photons, but for all interactions. Because fields propagate changes at finite speeds, and because the electromagnetic field's excitations define that speed, information carried by light sets the ultimate pace of cause and effect. This is not a technological limitation. It is a structural feature of reality. In this view, light is woven into the architecture of space-time itself. The electromagnetic field respects the symmetries of space-time, and those symmetries dictate how excitations behave. Lorentz invariance, a cornerstone of relativity, ensures that the laws governing light look the same to all observers moving at constant speeds. This invariance is not an added constraint. It is built into the field's very definition. There is a subtle pleasure in noticing how natural this all feels once it is absorbed. The universe is not a stage filled with actors. It is a network of fields, continuously interacting, continuously evolving. Light is one of the most accessible expressions of this network because it reaches us directly, carrying information without carrying matter. Even the darkness between stars becomes richer in this light. It is not a void, but a region where the electromagnetic field happens to be in a low energy state. That state still has structure, still fluctuates, still participates in the universe's dynamics. Light passing through that darkness is not moving through nothing. It is a modulation of what is already there, and so the fascination deepens, not as a sudden surge, but as a steady realization. Light, according to quantum field theory, is the electromagnetic field revealing its quantum nature. It is energy without substance, motion without mass, presence without material form. It is one of the clearest windows we have into how reality organizes itself at the most fundamental level, quietly glowing through the fabric of existence. That clarity invites another layer of fascination. Fascination. The electromagnetic field does not exist in isolation. It is part of a larger family of fields that together form what physicists call the quantum vacuum. Each field has its own character, its own way of being excited, yet they all share the same space-time. Light is one voice in a quiet chorus, distinct yet inseparable from the rest. When we look closely at how light propagates, quantum field theory tells us that it does so through the continuous reshaping of probability amplitudes. The field does not send a signal like a messenger running along a path. Instead, the likelihood of finding an excitation shifts smoothly from place to place. What we observe as a photon traveling is the evolving structure of that likelihood, guided by the equations of the field. There is something gently mesmerizing about this. Light is not pushed forward by momentum in the way a thrown stone is. It unfolds. Its future behavior is encoded in the present state of the field, and the symmetries it obeys. This unfolding is deterministic at the level of the field's evolution, yet probabilistic in how its excitations are detected. Both aspects coexist without tension. Quantum field theory also reframes the idea of boundaries. When light passes from one medium to another, such as from air into glass, it slows down. Not because the photon itself changes speed in a simple sense, but because the electromagnetic field interacts with the charged fields in the material. The excitation becomes a coupled motion, part field, part matter. This hybrid behavior is sometimes described as a quasi-particle, but at heart it is still the field responding to its environment. This response explains refraction, reflection, and dispersion with quiet precision. Different frequencies of light interact differently with matter, because the charged fields in atoms respond more readily to some oscillations than others. The colors separate, the angles shift, and the familiar optical effects emerge. Fascination. The beauty here is that nothing new needs to be added. The same field, the same rules, simply operating in a different context. At even deeper levels, quantum field theory reveals that the electromagnetic field itself is constrained by consistency. It must remain mathematically well-behaved, free of infinities that cannot be controlled. The techniques developed to handle these challenges, known as renormalization, once seemed artificial. Over time, they revealed something profound. Fields change their effective behavior depending on the scale at which they are examined. This means that light, as described by the electromagnetic field, subtly changes character depending on energy. At everyday scales, it behaves exactly as Maxwell's equations predict. At higher energies, quantum corrections become important. The field interacts with its own fluctuations, with virtual particles flickering in and out of existence. Fascination. This layered behavior suggests that what we perceive is only the low energy face of a much richer structure. The idea that fields are primary also reshapes how we think about causality. When an atom emits light, it is not sending a signal that propagates through emptiness until it reaches a target. It is initiating a change in the electromagnetic field that propagates according to strict rules. That propagation respects the causal structure of space-time. Effects never outrun causes. Light is the expression of that limit, the fastest way information can flow. There is a quiet sense of reassurance in this. The universe is not arbitrary. The behavior of light reflects deep consistency between quantum mechanics and relativity. Quantum field theory is the language that allows these two pillars to coexist. Light, massless and ever-moving, sits at their intersection, revealing how time, space, and energy are woven together. Even uncertainty takes on a softer tone here. The uncertainty in a photon's position or momentum is not a flaw in description. It is a natural feature of how field excitations are defined. A perfectly localized excitation would require infinite energy. The field does not allow that. Instead, it offers a balance, a spread that keeps everything finite and physically meaningful. Fascination. This balance is not imposed by hand. It arises from the structure of the field itself. The same principles that prevent infinities also ensure stability, allowing light to exist as a gentle, persistent presence rather than a violent disturbance. As these ideas settle, the question of what light is made of begins to feel almost misplaced. Light is not assembled from smaller components. It is an allowed pattern of activity, one of the simplest ways the electromagnetic field can express energy and momentum. Asking what it is made of is like asking what a vibration is made of. the answer is not substance, but structure. And that realization carries a calm satisfaction. Light is not a mystery object moving through an empty universe. It is the universe, or at least one of its fundamental fields, momentarily stirred. In that stirring, stars shine, atoms bond, eyes see, and knowledge travels across space and time, all through the same quiet, elegant framework that quantum field theory reveals. That sense of structure over substance carries a quiet, steady fascination. Fascination. It suggests that reality is less like a collection of things and more like a set of permissions, a list of allowed patterns that fields can adopt without breaking the underlying rules of the universe. In quantum field theory, the electromagnetic field is described by equations that are remarkably economical. They do not specify particles directly. They specify how the field can change, how it responds to charges, how it propagates through space-time. Photons appear not because they are inserted into the theory, but because the field, when quantized, naturally allows discrete excitations. Light is not assumed. It emerges. This emergence is one of the most quietly satisfying aspects of the theory. When the field is treated classically, it behaves like a smooth wave. When quantum principles are applied, the same field reveals a granular structure. Nothing fundamental is added or taken away. The shift happens entirely in how the field is allowed to behave. Fascination. The simplicity of that transition is easy to miss, but once seen, it feels almost inevitable. There is also a subtle humility built into this picture. Quantum field theory does not claim that fields are made of something else. It stops at fields. They are taken as fundamental, not because physicists believe they are the final answer, but because every attempt to go deeper has, so far, circled back to field-like descriptions. Light, as an excitation of a field, sits right at that boundary between what we can describe and what we can only infer. This becomes especially clear when considering attempts to unify physics. In many approaches to quantum gravity, space-time itself may emerge from something more basic. Even in those speculative frameworks, fields and their excitations often reappear in some form at low energies. Light persists as a pattern that survives deeper rewritings of reality. Fascination. It is as if the universe insists on expressing itself through fields, no matter how far down we look. Quantum field theory also reveals that light has no internal clock. Because photons are massless, they do not experience time in the way massive particles do. Along the path of a photon, from emission to absorption, the proper time is 0. This does not mean the journey is instantaneous in our frame, but it does suggest that light occupies a special role in the structure of space-time. It links distant events without aging between them. There is something quietly profound about this. A photon, emitted billions of years ago from a distant galaxy, arrives here without having experienced the passage of time. The electromagnetic field carried that excitation across the expanding universe, preserving its energy and momentum according to precise rules. Fascination. Light becomes a bridge not only across space, but across time itself. The field perspective also helps explain why light is so stable. Photons do not decay. There is no lower energy state for the electromagnetic field's excitations to fall into, short of being absorbed by matter. This stability is not accidental. It follows from the symmetries of the field and the conservation laws they imply. Energy, momentum, and angular momentum constrain what is possible, and light fits perfectly within those constraints. Even angular momentum takes on a new texture here. Photons can carry spin, a form of intrinsic angular momentum associated with their polarization. This spin is not the rotation of a tiny object. It is a property of the field's excitation, a reflection of how the field transforms under rotations in space. Fascination. The idea that rotation can exist without something rotating feels strange at first, yet it works, and it works with astonishing accuracy. The more one sits with this, the more light begins to feel less like an entity and more like an event that can be extended, that can interfere with itself, that can be delayed, redirected, or absorbed, but never truly stored as an object. Even when light is trapped in a cavity or slowed in a medium, what is stored is not a photon in a box, but energy shared between the electromagnetic field and matter fields. This shared behavior underscores another quiet insight. Light is relational. It only takes on meaning through interaction. A photon that is never absorbed, never scattered, never detected, leaves no trace. Its existence is defined by what it can do, not by what it is in isolation. Fascination. This aligns deeply with the field view, where states and interactions carry more weight than individual entities. Quantum field theory does not reduce light to something mundane. If anything, it elevates it. Light becomes a direct expression of the rules that govern reality at the deepest level we currently understand. It is the electromagnetic field behaving in its simplest quantum way, free to travel, free to carry information, constrained only by the symmetries of space-time. As these ideas continue to unfold, light feels less like an answer and more like a guide. By studying what light is made of, according to quantum field theory, we are really studying how the universe organizes itself, how it balances continuity and discreteness, how it allows change without chaos. Light is not a building block. It is a signature, a gentle trace of the field-based nature of everything that exists. That idea of light as a signature rather than a substance continues to open outward, carrying with it a steady, unforced fascination. Fascination. It suggests that when we observe light, we are witnessing the universe obeying its own rules with remarkable consistency, revealing not a material ingredient, but a principle in motion. Quantum field theory tells us that the electromagnetic field is defined everywhere, even where there are no sources, no charges, no currents. This universality is essential. It means that light does not need a medium to move through. There is no ether, no background substance vibrating beneath it. The field itself is the background, woven into space-time so completely that separating the two becomes impossible. This is why the speed of light is the same in all directions and for all observers. The electromagnetic field does not propagate through space. It propagates as space. Its excitations respect the geometry of space-time rather than traversing it like travelers on a road. Fascination. This dissolves one of the oldest intuitions in physics, the idea that motion requires something to move through. At very small scales, this picture becomes even more intimate. When physicists describe interactions between light and matter, they use diagrams, often called Feynman diagrams, that trace how field excitations influence one another. These diagrams are not literal pictures of particles flying around. They are visual representations of mathematical terms, bookkeeping tools that encode probabilities. Light, in these diagrams, appears as lines connecting events, not as tiny beads. It is the field's influence being accounted for step by step. There is something quietly beautiful about how these abstract representations translate into real predictions. From them emerge the precise rates at which atoms emit photons, the angles at which light scatters, the probabilities that govern every optical experiment. Fascination. The electromagnetic field, guided by quantum rules, becomes not just conceptually satisfying but numerically exact. This exactness has practical consequences that permeate daily life. The operation of semiconductors, the behavior of LEDs, the precision of atomic clocks, and the reliability of GPS systems all depend on the quantum field description of light and matter. These technologies work not because photons are little objects we can manipulate, but because the fields they belong to behave in predictable, stable ways. Quantum field theory also clarifies why light can be confined without being contained. In optical fibers, for example, light is guided along long distances with minimal loss. The electromagnetic field interacts with the material boundaries in such a way that certain modes are allowed to propagate while others are suppressed. The light is not trapped like water in a pipe. It is a pattern that persists because the field and the material conspire to support it. Fascination. This idea of supported patterns appears again and again in field theory. What exists is not what is possible in principle, but what is allowed by the structure of the system. Light persists where the conditions are right for its field excitations to remain coherent. At cosmological scales, the same field description holds. The cosmic microwave background is light, ancient light, released when the universe cooled enough for electrons and protons to form neutral atoms. That light has been traveling ever since, stretched by the expansion of space itself. Its wavelength has grown, its energy reduced, but its identity as an excitation of the electromagnetic field has remained intact. Fascination. The field remembers the early universe in the form of these gentle, lingering photons. This stretching of light reveals another subtle feature of quantum field theory. Energy is not always conserved in the simple, everyday sense when space-time itself is changing. In an expanding universe, the energy of photons decreases as their wavelength increases. The field adapts to the geometry it inhabits. This does not signal a failure of the theory. It reflects a deeper understanding of conservation laws in dynamic spacetime. Light, then, becomes a record keeper. Its properties encode information about the conditions under which it was emitted and the space through which it traveled. Spectral lines reveal the composition of stars. Redshifts reveal the expansion of the universe. Polarization patterns reveal primordial fluctuations. All of this information is carried not by objects, but by the state of a field. The fascination deepens when considering that the electromagnetic field does not exist alone. It interacts with other fields, some familiar, some still mysterious. Dark matter, whatever its nature, may interact weakly with the electromagnetic field or perhaps not at all. Dark energy shapes space-time in ways that affect how light propagates over cosmic distances. Light becomes a probe, a gentle interrogator of the universe's unseen components. Quantum field theory also provides a framework for understanding why light does not feel friction in a vacuum. There is no medium to resist it, no substance to sap its energy. The field's equations allow free propagation, limited only by interactions. When those interactions are absent, light continues unimpeded. Fascination. Motion without loss becomes not a miracle, but a natural consequence of the field's symmetry. Even the concept of brightness takes on a new meaning here. Brightness corresponds to how many excitations of the field are present, how densely packed the photons are. Intensity is not about how forcefully something is thrown, but about how populated a particular field state is. A dim light and a bright light differ not in kind, but in how much the field is excited. As this understanding settles, light feels increasingly less like a thing and more like a language. A language spoken by the electromagnetic field, conveying energy, momentum, and information across space and time. It is a language with strict grammar, enforced by quantum rules and relativistic symmetry, yet capable of infinite expression. And within that language, there is a quiet reassurance. The same rules apply everywhere. The same field exists everywhere. Light does not change its nature as it crosses the universe. It remains what it always is, an excitation of the electromagnetic field, precise, consistent, and endlessly revealing, a calm, luminous thread woven through the deepest fabric of reality. That sense of light as a language continues to deepen, and with it comes a soft, unmistakable fascination. Fascination. Because languages are not things you hold. They are systems of meaning, patterns that exist only when expressed. Light, in quantum field theory, is exactly that. A pattern that exists only while the electromagnetic field is speaking. This becomes especially clear when we think about how light carries information. Information is not embedded in photons as if they were envelopes. It is encoded in the state of the field. Frequency, phase, polarization, direction. These are not decorations added afterward. They are the defining features of the excitation itself. Change the pattern and the meaning changes. The field does not store messages. It becomes the message. When a radio antenna emits a signal, it does not send out little packets, labeled with data. It drives the electromagnetic field into a specific oscillatory pattern. That pattern spreads outward, reshaping the field everywhere it reaches. A receiving antenna resonates with that pattern and responds. What passes between them is not an object, but a shared field configuration unfolding across space. Fascination. Communication revealed as coordination rather than transfer. Quantum field theory also explains why light can interfere with itself. When two light waves overlap, their field amplitudes add together. In some places, they reinforce. In others, they cancel. This is not photons colliding or avoiding one another. It is the field obeying linear superposition. The excitation is not confined to a single path. It is distributed, and where distributions overlap, patterns emerge. At low intensities, this interference still occurs, even when light is emitted one quantum at a time. The field evolves smoothly. Detection happens discreetly. This dual behavior is not a contradiction. It is a reflection of the fact that the field's evolution and the act of interaction with matter are governed by different aspects of the same theory. Fascination. Smoothness and granularity coexist without conflict. The electromagnetic field also carries zero-point energy, even in its lowest state. This energy cannot be removed. It is a consequence of quantization itself. The field cannot be perfectly still, because perfect stillness would require infinite precision, which quantum mechanics forbids. This restless calm of the vacuum shapes how light behaves, how forces act at small distances, and how stability emerges from uncertainty. There is something quietly profound here. Even when no light is present, the conditions that allow light to exist are already in place. The field is poised, structured, alive with possibility. Light does not bring energy into a void. It reorganizes what is already there. Quantum field theory also helps explain why light does not have a size. Photons are not small in the way grains of sand are small. Their spatial extent depends on how they are prepared and measured. A photon emitted with a well-defined frequency is spread out over a long distance. One localized in time has a broad range of frequencies. This trade-off is not a limitation of technology. It is a fundamental feature of how field excitations are defined. Fascination. Light resists being boxed into simple spatial terms. It is neither point-like nor spread out by necessity. It takes the shape that the field and the interaction demand. When light is absorbed, it does not disappear into nothingness. Its energy and momentum are transferred to matter fields. An electron changes state. A molecule vibrates. Heat increases. The electromagnetic field relinquishes an excitation, and other fields gain energy. The total field content of the universe adjusts, conserving what must be conserved, transforming what is allowed to transform. This continuous reshuffling is the heartbeat of quantum field theory. Nothing stands alone. Fields exchange excitations. Light is one of the most mobile and expressive of these exchanges, but it is never separate from the whole. Even reflection becomes richer in this view. When light reflects from a surface, the electromagnetic field interacts with the charged fields in the material. Those charges respond, oscillate, and re-emit the field in a way that preserves energy and momentum. The reflected light is not the original photon bouncing back. It is a new excitation of the same field, shaped by the interaction. Fascination. Continuity without identity. The same is true for transmission. Light entering glass does not pass unchanged through a sea of atoms. It becomes a coupled excitation, part electromagnetic field, part material response. The field slows because it is sharing its energy with matter in a rhythmic exchange. When it exits, the electromagnetic field resumes free propagation. The light that emerges is continuous with what entered, yet not numerically the same excitation. This dissolves the everyday notion of tracking a single photon like a bead along a wire. Quantum field theory replaces that picture with something gentler and more precise. Excitations appear, transform, and dissolve according to rules that never privilege individuality over consistency. There is a calm beauty in how little excess this framework contains. No hidden machinery, no extra substances, just fields, symmetry, and quantization. Light emerges naturally, not as a special case, but as one of the simplest consequences of an electromagnetic field living in space-time. And as this understanding continues to settle, the fascination does not spike or demand resolution. It steadies. Light becomes familiar again, but in a deeper way. Not because it is ordinary, but because it fits. It belongs exactly where it is, doing exactly what the structure of reality allows it to do, glowing not as a thing, but as an ongoing expression of the field that fills the universe. That fittingness settles into a deeper, quieter fascination. Fascination. Because when something fits this well, it begins to feel less like a theory imposed on nature and more like nature gently explaining itself. Quantum field theory invites us to stop imagining light as something that moves through space, and instead see it as something space allows. The electromagnetic field does not sit inside space-time like a substance in a container. It is defined at every point of space-time, inseparable from the coordinates that describe where and when events occur. Light is what happens when that inseparability becomes dynamic. This perspective subtly changes how motion itself feels. When light propagates, the field does not push an excitation forward step by step. The equations describe how the field's configuration at one moment determines its configuration at the next. There is no preferred location where the photon is hiding between interactions. There is only the evolving state of the field, smooth and lawful, unfolding according to symmetry. Fascination. The absence of a hidden trajectory can feel unsettling at first, but it carries a kind of peace. Nothing is lost between emission and absorption. Nothing needs to be tracked. The field simply evolves. This evolution is deeply constrained. The electromagnetic field must respect conservation laws that arise from symmetry. Energy conservation comes from time symmetry. Momentum conservation comes from spatial symmetry. These are not separate rules layered on afterward. They are consequences of how the field is allowed to exist. Light inherits these constraints automatically, not as a burden, but as a natural expression of order. Even randomness takes on a softer meaning here. The probabilistic nature of photon detection does not imply chaos or ignorance. It reflects the fact that the field's state contains many possibilities at once, and interactions select among them. Probability is not a failure of knowledge. It is a feature of how quantized fields behave. There is a gentle sense of wonder in realizing that this probabilistic structure is exact. The rules governing it are precise enough to predict experimental outcomes with extraordinary accuracy. The apparent looseness of probability rests on an underlying rigidity of form. Quantum field theory also clarifies why light does not accumulate scars from its journey. A photon traveling through empty space does not wear down or age. There is no internal clock ticking, no internal structure to distort. The electromagnetic field's excitation remains what it is until an interaction changes it. Fascination, persistence without memory. When light does interact, those interactions are local. The field at one point influences the field nearby. Nothing jumps ahead. This locality preserves causality and ensures that the universe remains intelligible, even as it operates through abstractions that stretch intuition. This locality also explains why shielding works. Materials block light not by stopping photons as objects, but by forcing the electromagnetic field into configurations that cannot propagate through. The field adapts, reflects, dissipates, or converts energy into other forms. Light yields not because it is weak, but because the field respects the constraints imposed by matter. The more one sits with this, the clearer it becomes that light is not exceptional. It is exemplary. It shows how quantum fields behave in their simplest form: massless, linear, symmetric. Other fields are more complex, more tightly bound, more hidden. Light is generous. It reveals itself readily. Fascination. It is the easiest field to observe and the hardest to reduce to an object. Quantum field theory also offers a gentle answer to why light feels so immediate. There is no delay in its essence, only in its propagation. The moment a photon is absorbed, the electromagnetic field locally changes state. There is no residual light waiting to finish its journey. The process is complete. Even the idea of simultaneity becomes subtle here. Different observers may disagree on when events occur, but the field's laws remain consistent across all frames. Light respects that consistency. It does not privilege any single viewpoint. It behaves the same for all observers in uniform motion, not by choice, but by necessity. This impartiality gives light a kind of neutrality. It carries information without bias. It reveals without interpreting. What it shows depends entirely on how it is prepared and how it is received. The field does not embellish, and yet the consequences are rich. Through light, we infer the temperatures of stars, the motions of galaxies, the fingerprints of atoms. All of that information arrives encoded in the simplest possible excitations of a single field. Fascination. Immense complexity riding on minimal structure. As these ideas continue to flow, the original question transforms. What is light made of becomes less about composition and more about permission. Light is made of what the electromagnetic field is allowed to do when quantized. It is made of symmetry, of consistency, of the quiet insistence that reality obey its own rules everywhere, without exception. And in that insistence, light continues to move, not as a thing crossing space, but as space itself briefly leaning into motion, carrying energy and meaning along paths that are written into the deepest fabric of existence. That permission-based view continues to resonate, settling into an even calmer fascination. Fascination. Because it implies that light does not need motivation, origin stories, or mechanical explanations. It simply follows from what the electromagnetic field is allowed to be. Quantum field theory treats the field as an operator, something that can change states, something that acts on the space of possibilities. Light appears when the field transitions between these states. This language can sound abstract, but its consequences are tangible. It predicts exactly how much energy light carries, how it transfers momentum, how it interacts with charges. The abstraction is not a retreat from reality. It is a refinement of how reality is described. There is something quietly reassuring about how little excess there is in this description. No gears turning behind the scenes, no hidden substances, just a field, symmetry, and quantization. Light becomes a necessary consequence rather than a special case. This necessity is why light appears wherever charged matter exists. Whenever electrons move, whenever atoms rearrange, whenever energy shifts between states, the electromagnetic field responds. Light is not summoned. It emerges. Fascination. The inevitability of it feels almost gentle. Quantum field theory also removes the idea of absolute emptiness from the universe. Even in regions where no light is present, the electromagnetic field exists in its ground state. This ground state is not silent. It fluctuates. These fluctuations are constrained, structured, and real. They shape how light behaves when it appears and how matter behaves even when it does not. The presence of these fluctuations means that light is never traveling through a neutral backdrop. It moves through a field that already has texture. That texture is subtle, but it leaves fingerprints. Tiny shifts in energy levels, small forces between objects, slight corrections to particle properties. Light carries those fingerprints with it, shaped by the field's ever-present activity. Fascination. The vacuum is not a stage waiting for actors. It is already performing. When light propagates freely, its behavior is governed by the simplest possible field equations. These equations do not dissipate energy. They do not introduce friction. They preserve form. This is why light can travel across billions of years without fading. Not because it is indestructible, but because the field does not require it to change. Only interaction brings a change. When light meets matter, the field couples. Energy flows. Momentum is exchanged. States shift. The field reorganizes. Nothing mystical. Nothing arbitrary. just consistent evolution. This consistency is what allows us to trust light. When astronomers analyze light from distant galaxies, they rely on the fact that the electromagnetic field behaves the same there as it does here. Quantum field theory guarantees that. The field does not evolve differently in different places. Its rules are universal. Fascination. The universe speaks one electromagnetic language everywhere. Even time itself feels different in this context. Because photons do not experience proper time, light does not age. It carries information across eras without distortion from internal processes. A photon emitted in the early universe arrives with its message intact, altered only by the geometry of space-time through which it traveled. This gives light a peculiar role as a cosmic archivist. It preserves the conditions of its birth, temperature, density, motion, all encoded in frequency shifts and polarization patterns. Light does not remember in the human sense, but it retains structure with astonishing fidelity. Quantum field theory also clarifies why light is so deeply tied to measurement. Many detectors rely on electromagnetic interactions. To observe is often to absorb light. Measurement becomes an exchange of field excitations. The observer is not outside the system. They are another configuration of fields interacting locally. Fascination. Observation revealed as participation. This dissolves the idea of a sharp boundary between observer and observed. Light mediates between systems, allowing information to flow without transferring matter. It is the cleanest channel nature provides, and quantum field theory explains why. The electromagnetic field couples universally to charge and remains otherwise unburdened. As these ideas continue to unfold, light feels less like a topic and more like a lens. Through it, quantum field theory becomes intuitive, almost familiar. Fields are not exotic once light is understood this way. They are simply the most efficient way to describe how reality behaves. Light is not built from pieces. It is not assembled. It is allowed. Allowed by symmetry, allowed by quantization, allowed by the structure of space-time itself. And in that allowance, light continues to appear wherever energy shifts, wherever matter moves, wherever the electromagnetic field finds reason to stir. Quietly, reliably, carrying no substance, yet shaping everything it touches. A steady, luminous expression of the deepest rules the universe follows. That steadiness deepens into a quieter kind of fascination, the sort that does not sparkle but endures. Fascination. Because the more closely light is examined through quantum field theory, the more it seems to withdraw from the category of things and settle firmly into the category of behavior. The electromagnetic field does not possess texture or color or brightness on its own. Those qualities emerge only when the field is excited in specific ways and interacts with matter prepared to respond. Light is not luminous by itself. It becomes luminous in relation. This relational nature is not philosophical ornamentation. It is built directly into the mathematics of the field. When the field is quantized, its excitations are counted not by shape or size, but by mode. A mode is a way the field can oscillate while respecting boundary conditions and symmetry. Each mode behaves like an independent harmonic oscillator. This is one of the most quietly elegant aspects of quantum field theory. Light is made of modes being excited, one quantum at a time. Fascination. A beam of light is not a stream of objects. It is a population of excited modes, coexisting, overlapping, and evolving together. This modal picture explains why light can be decomposed so cleanly into frequencies. Fourier analysis is not just a mathematical trick. It reflects something real about the field. The electromagnetic field naturally organizes itself into oscillatory components. Each component corresponds to photons of a particular energy. Color emerges from structure, not from substance. Even white light becomes understandable this way. It is not a special kind of photon. It is a superposition of many field modes excited simultaneously. The eye and brain perform their own form of field analysis, responding differently to different frequencies and assembling the experience of color from those responses. Quantum field theory also reveals why light feels so effortless. There is no resistance to its propagation in vacuum, because there is no mechanism within the field equations that would damp it. Dissipation requires coupling. In empty space, the electromagnetic field has nothing to couple to strongly enough to lose energy. It persists because nothing compels it to change. This persistence is not stubbornness. It is neutrality. The field does exactly what the equations allow and nothing more. Light travels because the equations permit traveling solutions. It does not seek destinations. It unfolds. Fascination. Motion without intent, yet perfectly ordered. When boundaries appear, the field adapts. Mirrors, lenses, cavities, waveguides. These do not manipulate photons like tools handling parts. They impose conditions on the field, reshaping which modes are allowed. Reflection and refraction emerge from constraint, not collision. This makes optical devices feel less like machines and more like sculptors of possibility. They do not grab light. They guide which field patterns can exist within them. Quantum field theory also clarifies why there is no absolute distinction between near and far. The electromagnetic field connects regions of space through local interactions, yet the patterns it supports can span vast distances. A single excitation can be delocalized across kilometers or light years. Localization happens only when interaction demands it. Fascination. Distance becomes secondary to structure. At the smallest scales, the electromagnetic field is inseparable from quantum uncertainty. Attempting to pin down a photon's position increases uncertainty in its momentum. Attempting to specify its energy precisely stretches it in time. These trade-offs are not inconveniences. They are the field protecting its consistency. The field does not allow contradictions. It balances precision across complementary descriptions. Light exists only where that balance is respected. This balance also explains why classical electromagnetism works so well. At large scales, with many excitations present, quantum fluctuations average out. The field behaves smoothly. Waves emerge naturally. The classical picture is not wrong. It is the large-scale limit of the quantum field description. Fascination. Smoothness revealed as a collective effect. The electromagnetic field does not need interpretation to function. It does not require observers. Light existed long before eyes evolved to receive it. It illuminated nothing and yet filled the universe. Only later did matter arrange itself into forms capable of responding to it in ways we now call seeing. This gives light a quiet independence. It is not defined by perception. Perception is defined by how it interacts with light. Quantum field theory also removes any sharp line between radiation and matter interaction. Absorption and emission are symmetric processes. Time reversal symmetry ensures that what can happen one way can, in principle, happen the other. Light and matter exchange roles fluidly within the constraints of energy and momentum. Fascination. Roles without hierarchy. As the understanding continues to deepen, light becomes less mysterious in the sense of being confusing, and more mysterious in the sense of being fundamental. It is simple without being shallow, familiar without being reducible. Light is not built from smaller things. It is not assembled. It is permitted. It exists because the electromagnetic field exists, because that field can be excited, and because space-time allows those excitations to propagate. And so light continues everywhere, not as a substance moving through emptiness, but as emptiness itself briefly taking on structure, carrying energy and information with perfect obedience to the quiet rules that govern all fields, glowing not loudly, not urgently, but steadily, as one of the clearest expressions of how reality chooses to be. That steadiness invites the mind to rest even deeper into the idea, and from there another layer of fascination quietly appears. Fascination. Because light, understood this way, no longer feels like something added to the universe. It feels like something the universe cannot avoid producing. Quantum field theory suggests that once the electromagnetic field exists, light is inevitable. Any change in charged matter disturbs the field. Any disturbance propagates. Any propagation, when quantized, appears as photons. There is no extra step where light is manufactured. It is the automatic response of the field to change. This inevitability explains why light permeates so many physical processes. Heat radiates, charges accelerate, atoms transition. The electromagnetic field responds every time. Light is not rare, it is constant. What varies is whether there is something nearby to notice it. Even when no light is detected, the field retains its readiness. The ground state is stable but not inert. The possibility of excitation is always present. This gives the universe a kind of quiet alertness. Nothing is happening, yet everything is prepared to happen. Fascination. Potential built directly into existence. Quantum field theory also reveals that light does not require continuity of material support to remain coherent. A photon emitted from an atom does not rely on a chain of interactions to keep going. Once the field is excited, the excitation propagates according to the field's own rules. Matter may create light and absorb it, but light does not depend on matter to persist in between. This independence is what allows light to cross intergalactic space, where matter is sparse beyond imagination. The electromagnetic field remains. Its excitations remain allowed. Light continues. The field perspective also dissolves the idea of edges. There is no boundary where light stops being light and becomes something else. Its frequency can stretch, its energy can shift, its direction can bend. But its identity as a field excitation remains intact. Even when light becomes so low in energy that it merges with background radiation, it has not ceased to exist. It has blended. Fascination. Identity without sharp borders. When physicists speak of photons being created or destroyed, this language can sound dramatic. In the field picture, nothing abrupt occurs. The field transitions between states. Excitations appear when energy is transferred in. They disappear when energy is transferred out. Creation and annihilation are bookkeeping terms for changes in field configuration. This gentler interpretation matters. It removes violence from the microscopic world. There are no tiny collisions or shatterings. There are only smooth, lawful transitions. Even quantum jumps in atoms, once imagined as sudden leaps, are understood as interactions mediated by fields. The atom and the electromagnetic field evolve together, exchanging energy until a stable configuration is reached. Light emerges as part of that shared evolution. Fascination, change without rupture. Quantum field theory also explains why light has no preferred scale. It can be as energetic as gamma rays or as gentle as radio waves. The field supports excitations across an enormous range of frequencies. This scale freedom is a direct consequence of the field's linearity and masslessness. There is no built-in length or energy scale that limits light. This absence of scale gives light its universality. It can probe atomic structures and cosmic horizons with the same underlying rules. Few phenomena enjoy such reach. At the same time, the field is disciplined. Not every excitation is allowed. Boundary conditions, conservation laws, and symmetry restrict what Kinsey field configurations can exist. Light is free, but not arbitrary. It explores possibility within structure. Fascination. Freedom constrained by order. The more this picture settles, the more the word "made of" begins to feel out of place. Light is not composed. It is configured. It is a state of the electromagnetic field that carries energy and momentum in the only way that field knows how. Even calling photons particles feels provisional here. They behave like particles in detectors because interactions are localized. They behave like waves in propagation because the field evolves smoothly. Both behaviors are surface expressions of something deeper and more unified. Quantum field theory does not ask us to choose between wave and particle. It shows that both are approximations of field behavior under different conditions. Light is neither. It is the field itself, momentarily articulate. Fascination. Categories dissolving into consistency. As this understanding continues to unfold, light becomes less mysterious in the sense of being puzzling, and more mysterious in the sense of being fundamental. It is simple because the rules are simple. It is profound because those rules reach everywhere. Light is not a substance drifting through emptiness. It is emptiness structured. It is space-time hosting an electromagnetic field that cannot help but express itself when energy flows. And so the electromagnetic field continues, everywhere, quietly present, quietly active. Whenever it stirs in its quantized way, light appears. Not as a thing sent from here to there, but as the universe momentarily revealing how it moves energy and information without ever needing to move. Matter, a soft, luminous trace of the deepest order beneath everything we see. That softness continues to deepen, and with it comes another quiet surge of fascination. Fascination. Because at this point, light no longer feels like something that needs explaining. It feels like something that explains. Quantum field theory reveals light as one of the clearest demonstrations that reality is built from rules rather than materials. The electromagnetic field exists because the universe allows a field with that symmetry to exist. Once it exists, everything that follows, photons, radiation, illumination, communication, is simply the field behaving honestly. There is no hidden engine behind light. No internal mechanism ticking away. Its behavior is entirely contained in how the field is allowed to evolve from one moment to the next. This makes light profoundly transparent in a conceptual sense. It hides nothing behind itself. Fascination, a phenomenon that reveals rather than conceals. Even when light seems complicated, when it scatters, diffracts, polarizes, or entangles with matter, the complexity arises not from internal structure, but from interaction. The electromagnetic field meets other fields. Boundaries appear. Constraints multiply. Patterns grow richer. Light remains what it always was, but the context becomes elaborate. Quantum field theory also clarifies why light is such a reliable probe. Because the electromagnetic field couples in a well-understood way to charged matter, light carries information faithfully. Its interactions are predictable. Its distortions are interpretable. This reliability is not an accident. It is the direct result of the field's simplicity and symmetry. Fascination. Trust emerging from minimalism. Even quantum entanglement involving light fits naturally into this picture. When photons become entangled, it is not because two particles are mysteriously connected across space. It is because the electromagnetic field is in a joint state that cannot be factored into independent pieces. The field does not assign separate realities where none exist. It maintains coherence across distance without violating locality. Measurement breaks that coherence not through magic, but through interaction. When the field couples to matter in a way that distinguishes outcomes, the joint state resolves into a specific configuration. Light does not choose. The field responds. This relational view dissolves much of the strangeness often attributed to quantum behavior. Light is not strange because it is unpredictable. It is strange only if we insist on forcing it into the mold of objects. As a field excitation, its behavior is not strange at all. It is exact. Fascination. Precision mistaken for mystery. Quantum field theory also shows why light feels weightless yet carries momentum. Momentum is not tied to mass. It is tied to how a field's energy flows through space. The electromagnetic field transports energy, and that transport necessarily involves momentum. When light strikes a surface, the field transfers that momentum. Nothing collides. The field simply rearranges. This rearrangement is enough to move mirrors, bend sails, and subtly alter orbits. Light shapes matter without touching it in any material sense. Fascination. Influence without substance. Even the concept of brightness becomes gentler here. Brightness is not force, it is population. Many excitations occupying the same or nearby modes. A bright light is not aggressive, it is abundant. And abundance in quantum field theory does not overwhelm the rules. Many photons can occupy the same state precisely because they are field excitations, not objects competing for space. This is why lasers work. This is why coherence can grow rather than collapse under repetition. Fascination. Order amplified by sameness. As the field picture settles fully into place, it becomes clear that asking what light is made of is like asking what a note is made of in music. The answer is not wood or metal or air. The answer is vibration structured by constraints. Light is vibration structured by the electromagnetic field and the geometry of space-time. There is no deeper layer where photons dissolve into smaller pieces. If such a layer exists, it does not reveal itself at energies we can probe. At every accessible scale, light remains an excitation of a field, complete in itself, requiring no internal scaffolding. This completeness gives light a kind of quiet dignity. It does not need elaboration. It does not need metaphor. It stands as one of the simplest, cleanest expressions of how quantum fields behave. Fascination. Simplicity that does not run out. And so light continues to appear wherever the electromagnetic field is disturbed, wherever energy flows through charged matter, wherever the universe reshapes itself even slightly. It appears without announcement, travels without effort, and vanishes without residue, leaving only redistributed energy and new configurations of fields behind. Not a thing sent from place to place. Not a substance poured through space. but a pattern allowed by symmetry, carried by a field that exists everywhere at once, quietly revealing that at the deepest level we know, reality is not made of objects at all, but of fields doing exactly what they are permitted to do, and light is one of the clearest ways they let us see that. That realization settles in gently, and from it arises another calm wave of fascination. Fascination. Because when light is understood this way, it becomes impossible to separate physics from meaning. Not meaning imposed by us, but meaning that comes from structure itself. Quantum field theory shows that the electromagnetic field does not wait for permission to exist. It is not switched on by stars or lamps. It is part of the universe's baseline description. Light appears not because the field is activated, but because it is never inactive. Excitations are simply moments when the field's ever-present potential becomes visible. This helps explain why light feels so immediate. When a lamp turns on, nothing travels instantly from the switch to your eyes. The field adjusts. Local excitations propagate. The response is swift because the field is already there, already connected. Light does not build a bridge. It reveals one that was always present. Fascination. Connectivity without construction. In quantum field theory, fields do not occupy space the way objects do. They define what space is allowed to do. The electromagnetic field assigns degrees of freedom to every point in space-time. Those degrees of freedom can change, oscillate, exchange energy. Light is what those changes look like when they organize into traveling patterns. This perspective removes any lingering sense that light is foreign to space. It belongs to space as deeply as geometry belongs to shape. When space exists with electromagnetic symmetry, light is unavoidable. Even silence in this context becomes meaningful. A region with no photons is not empty. It is the electromagnetic field in its lowest energy configuration. That configuration is stable, structured, and ready. Light is the field choosing, or rather being allowed, to move away from that quiet baseline. Fascination. Silence with depth. Quantum field theory also reveals why light is so difficult to stop without absorption. There is no friction term in the fundamental equations. To remove light, something must interact with it. Something must take its energy. Until that happens, the excitation persists. Light does not fade because fading would require a mechanism the field does not possess on its own. This is why darkness is not the gradual death of light, but simply the absence of interaction. Light either is or is not. It does not decay into nothingness. When absorption occurs, the process is exact. The electromagnetic field relinquishes an excitation. Another field gains energy. The universe's accounting remains precise. Nothing leaks, nothing vanishes. Fascination. Clean exchanges in a restless universe. The field view also clarifies why light can be redirected without being consumed. Lenses and mirrors do not steal energy. They impose constraints. They alter which field configurations are allowed to propagate. Light bends because the field adapts to new conditions, not because it is pushed. This adaptability gives light its grace. It does not resist redirection. It simply reorganizes. Quantum field theory further explains why light does not carry entropy in the way matter does. A photon can be created in a highly ordered state, such as in a laser, and remain ordered over long distances. Disorder enters only through interaction. The field itself preserves coherence unless something intervenes. Fascination. Order without effort. This preservation of coherence allows light to function as a clock, a ruler, a carrier of phase. Atomic transitions define time standards. Interference defines distance. All of this relies on the field's unwavering consistency. Light does not drift from its rules. The deeper one goes, the more it becomes clear that light is not one phenomenon among many. It is a reference. It sets scales. It defines limits. It anchors the structure of space-time. Even causality itself is traced along light cones. The paths field excitations are allowed to follow. Fascination. Boundaries written in brightness. Quantum field theory does not romanticize light, but it does place it at the heart of reality's organization. Light is how the electromagnetic field communicates change. It is how energy moves without mass. It is how information crosses distance while respecting causality. And perhaps most quietly striking of all, light requires no interpretation to function. Long before there were observers, before atoms formed, before matter cooled into structure, the electromagnetic field existed. When conditions allowed, light emerged. It did not wait to be seen. The universe was luminous before it was watched. This gives light a kind of independence that feels almost gentle. It does not depend on perception. Perception depends on it. Light does not exist to reveal. It reveals because that is what its field does when excited. As this understanding continues to settle, the original question fades into something softer. What is light made of becomes less important than what light demonstrates. It demonstrates that reality is not assembled from pieces, but organized by fields. That motion does not require substance. That connection does not require contact. Light is the electromagnetic field briefly departing from stillness, carrying energy and momentum in the only way it can, according to rules that are everywhere the same, rules that do not strain or rush, rules that simply allow patterns to move. And in that allowance, light continues to flow through the universe, not loudly, not urgently, but faithfully, tracing the invisible structure of reality with quiet precision, leaving behind not fragments, but understanding, one excitation at a time. That faithfulness continues, and with it comes another gentle swell of fascination. Fascination. Because light, once seen through quantum field theory, begins to feel like the most honest thing the universe does. There is no pretense in light. It does not disguise complexity behind form. It does not require interpretation to justify itself. It exists because the electromagnetic field exists, and the field exists because the structure of reality allows it. Nothing more is needed. Quantum field theory teaches that the electromagnetic field is not something that emerged late in cosmic history. It is woven into the earliest moments we can meaningfully describe. As soon as space-time itself became a useful concept, the field was there, defined at every point, carrying within it the possibility of light long before light could freely travel. For a time in the early universe, matter and radiation were tightly coupled. Photons could not move far without interacting. The field was active, excited, yet confined. Then, as the universe expanded and cooled, a transition occurred. Electrons bound to nuclei. Matter became neutral. The electromagnetic field was suddenly free to support long-range excitations. Light decoupled and began its long journey. Fascination. A field gaining freedom as conditions quietly changed. This moment did not create light. It revealed it. The field did not switch on. It was simply no longer constrained. That distinction matters. It reminds us that light is not a substance waiting to be released. It is a pattern waiting to be permitted. Quantum field theory also shows why light does not fragment as it travels. There is no internal structure to break apart. A photon does not wear down or split unless the field interacts strongly enough with something else to allow such a process. In free space, nothing pulls light apart because there is nothing inside it to unravel. This lack of internal complexity gives light its extraordinary reliability. It carries energy across unimaginable distances without distortion from within. Any change it undergoes comes from external structure, from space-time curvature, from interaction with matter, from expansion itself. Fascination, purity of transmission. The electromagnetic field also respects a deep balance between freedom and restraint. It allows propagation, superposition, and coherence, yet forbids superluminal signaling, arbitrary amplification, or spontaneous decay. These prohibitions are not rules tacked on afterward. They are consequences of the field's symmetry and quantization. Light obeys these constraints effortlessly. It never strains against them. It simply unfolds within them. This is why light feels so natural as a reference. We define meters by how far light travels. We define seconds by frequencies of atomic transitions mediated by light. We define causality by light cones. The electromagnetic field anchors our measurements because it is stable, universal, and exact. Quantum field theory does not elevate light out of sentiment. It elevates it out of convenience. Light is central not because we chose it, but because the universe did. Fascination, centrality without ego. Even the idea of illumination becomes more subtle here. Light does not reveal objects by touching them. It reveals by interaction. The electromagnetic field couples to charged constituents of matter. That coupling reshapes both field and matter locally. The information carried away is not a photograph of the object, but a record of how the object allowed the field to respond. Seeing is a negotiation between fields. This makes perception feel less like passive reception and more like participation in a larger field-based conversation. The eye does not capture light. It joins an interaction that has already been unfolding across space. Quantum field theory also removes any sharp line between classical light and quantum light. The difference is not in kind, but in scale and context. A bright beam contains many excitations. A dim beam contains few. The underlying field is the same. The rules are the same. The behavior shifts smoothly. Fascination, continuity across regimes. As this understanding deepens, light becomes an anchor point for intuition about all quantum fields. Once it is clear that light is not made of pieces, it becomes easier to accept that electrons, quarks, and even more elusive entities are not tiny objects either. They are excitations, patterns, permissions realized. Light simply shows this most clearly because it is unburdened by mass. Quantum field theory does not ask us to imagine hidden machinery. It asks us to accept that the universe may be simpler than our metaphors. Fields exist. They evolve. Excitations appear and disappear. Nothing more is required. Light is the electromagnetic field expressing that simplicity with unmatched clarity. And so it continues, everywhere and always, not because it must be pushed, not because it seeks destinations, but because the field allows movement and space-time allows propagation. Light flows along the contours of possibility, guided by symmetry, restrained by causality, carrying energy without weight and information without substance. Not an object crossing a void, not a wave in a medium, But the electromagnetic field itself momentarily stirred, revealing through its motion the quiet, disciplined elegance of the universe beneath all appearances. That elegance continues to reveal itself, and with it comes another quiet moment of fascination. Fascination. Because the deeper the field-based picture settles in, the more light begins to feel like a principle rather than a phenomenon. Quantum field theory shows that light does not require substance to exist, only permission. Permission granted by symmetry, by the structure of space-time, and by the presence of the electromagnetic field. Once those conditions are in place, light is not optional. It is inevitable. This inevitability reframes how we think about illumination. When a star shines, it is not producing light as a product. It is undergoing processes that disturb the electromagnetic field. The field responds. Light appears. The star does not manufacture photons the way a factory produces objects. It participates in a field interaction that naturally results in radiation, fascination, production replaced by response. Even the idea of direction becomes softer here. Light does not choose a path. The field evolves according to local rules, and what we call a path is a pattern that emerges from that evolution. Rays are approximations. They are useful, but they are not fundamental. At the deepest level, there is only the field reshaping itself from one configuration to the next. Quantum field theory also clarifies why light does not pile up or clog space. Field excitations can overlap freely. Many photons can occupy the same region without crowding, because they are not objects with volume. They are states of a field. Space does not fill up with light. It hosts it. Fascination. Abundance without congestion. This property allows the universe to be luminous without being dense. Entire galaxies can shine without saturating the space between them. The electromagnetic field carries all of it effortlessly. When light interacts with matter, it does so selectively. The field couples to charge, to currents, to specific transitions. It does not interact indiscriminately. This selectivity gives rise to transparency and opacity, reflection and absorption. Materials are not solid barriers to light. They are structured environments that allow some field configurations and suppress others. This structured response is why glass can be transparent while metal is reflective, why the atmosphere filters some wavelengths and passes others. Light reveals material structure because it must negotiate with it. Fascination. Structure responding to structure. Quantum field theory also explains why light can be slowed without being damaged. In certain materials, light's group velocity decreases dramatically. The electromagnetic field shares its excitation with the material's fields. Energy oscillates between them. The combined system evolves more slowly. When the excitation is released, light resumes its usual behavior. Nothing about light is harmed in this process. The field remains consistent. Only the context changes. This contextual sensitivity makes light an exquisite probe. It responds to environments without losing its identity. It adapts without degrading. At the most fundamental level, the electromagnetic field does not care whether it is being used for vision, communication, or measurement. It does not privilege any application. It obeys its equations. Everything else is consequence. Fascination. Neutrality giving rise to meaning. Quantum field theory also removes the need for imagining light as a courier carrying packets of energy. Energy is not contained in photons like liquid in bottles. Energy is a property of the field's state. When that state changes, energy flows. Photons are how that flow is quantized, not how it is packaged. This makes emission and absorption feel less like exchange and more like reconfiguration. The field adjusts. Matter adjusts. The total arrangement shifts. Even the term photon becomes less central here. It is useful, precise, and real, but it is not primary. The field is primary. The photon is a convenient label for one unit of excitation. Focusing too much on the photon can obscure the deeper continuity of the field itself. Fascination. Labels dissolving into process. As the understanding deepens, it becomes clear that light is not something added to space after the fact. It is one of the ways space expresses what it already contains. The electromagnetic field is part of the universe's grammar. Light is one of its simplest sentences. This grammar is spoken everywhere, at all times, without accent or variation. The same electromagnetic field that governs light in a laboratory governs light between galaxies. Quantum field theory insists on this uniformity, and experiment confirms it again and again. There is a quiet comfort in that. The universe is not patchwork. Its rules do not change with location. Light does not have regional dialects, and so the electromagnetic field continues to exist, everywhere at once, never turning off, never resting, even in its quietest state. When it is excited in its quantized way, light appears. When it relaxes, darkness returns, though the field remains. Light is not made of pieces. It is not built from components. It is the electromagnetic field briefly arranged into motion, carrying energy and information along paths defined by space-time itself, revealing not a substance, but a principle, one that quietly underlies every glow, every reflection. Every moment the universe becomes visible to itself. That principle, like quality, continues to settle, and with it arrives another quiet pulse of fascination. Fascination. Because when light is understood this way, it becomes clear that it is not something the universe carries, but something the universe does. Quantum field theory invites us to see the electromagnetic field as a kind of readiness, a set of possibilities defined at every point in space-time. Light is what happens when that readiness is gently activated, not violently, not suddenly, simply according to the rules that have always been there. This helps explain why light never feels forced. Even in the most intense radiation, even near the most energetic events, light obeys the same calm structure. Gamma rays from a supernova and radio waves from a whispering antenna are expressions of the same field, separated only by how tightly or loosely the field is excited. Fascination. Extremes unified by a single description. Quantum field theory also shows that light does not have individuality in the human sense. There is no biography attached to a photon, no identity that persists beyond interaction. When an excitation is absorbed, it does not leave behind a trace of itself. The field simply moves on in a new configuration. This can feel counterintuitive at first, but it carries a quiet elegance. Nothing accumulates. Nothing clutters reality. The field remains clean, responsive, adaptable. The electromagnetic field also does not distinguish between near and far in any privileged way. Local interactions propagate outward according to the same rules everywhere. The field does not know whether a disturbance came from a nearby lamp or a distant quasar. It responds locally, and the pattern spreads. Fascination. Distance stripped of importance. This universality explains why light can be trusted as a messenger. The field does not distort its own excitations. Any distortion comes from interaction with matter or space-time geometry. When those influences are understood, the original signal can often be reconstructed. Light becomes a reliable witness. Quantum field theory also removes the need to imagine photons weaving their way through obstacles. When light passes through a medium, it is not dodging atoms. The field is interacting collectively with many charges at once. The result is an effective change in propagation, not a series of collisions. This collective behavior makes light smoother than any particulate picture could suggest. It glides through matter where allowed, reflects where constrained, and transforms where coupling demands. Fascination. Smoothness born from collectivity. At the deepest level, the electromagnetic field is defined by its symmetries. Gauge symmetry ensures that only certain combinations of field values have physical meaning. This symmetry is not decorative. It is what guarantees the existence of light itself. Remove it, and the photon disappears from the theory. This is one of the most quietly astonishing facts in modern physics. Light exists because the universe allows a particular kind of mathematical freedom. A freedom that has no direct sensory analog, yet manifests as illumination everywhere. Fascination. Existence born from symmetry. Quantum field theory also clarifies why light does not reveal everything. The electromagnetic field couples only to electric charge. Neutral particles may pass unnoticed. Dark matter, if it exists, as current theories suggest, may remain invisible precisely because it does not disturb this field. Light is honest, but it is selective. This selectivity is not a limitation. It is a clue. It tells us what kinds of structure exist and what kinds remain hidden. Light maps the charged universe. Other fields may map others. As this understanding deepens, light becomes a guide rather than a subject. It shows how fields behave. It shows how interactions unfold. It shows how simplicity can generate richness without complication. Quantum field theory does not claim to be the final word. It leaves open the possibility that fields themselves may emerge from something deeper. Yet, whatever that deeper layer may be, it must reproduce the electromagnetic field and its excitations. Because light is too consistent, too universal, too deeply woven into observation to be accidental. Fascination. Robustness across theories. So light continues to appear, not as a thing launched into space, but as space itself briefly articulating energy. It appears wherever the electromagnetic field is nudged away from its quiet baseline. It travels wherever space-time allows propagation. It vanishes wherever interaction reshapes the field again. No pieces, no carriers, no hidden machinery. Just a field, everywhere present, momentarily stirred into motion. And in that motion, the universe reveals itself, not through objects moving in emptiness, but through patterns unfolding in a field that never leaves, never exhausts itself, never needs to be replenished, a field whose simplest excitations we call light, and whose quiet, disciplined behavior continues to illuminate not only the world around us, but the deeper structure beneath it, one gentle excitation at a time. That request carries us naturally forward, into the next unfolding layer, without closure, without an ending, just deeper continuity. There's another quiet realization waiting here, and it arrives with a soft but unmistakable fascination. Fascination. Because once light is understood as a field excitation rather than a thing, the boundary between existence and activity begins to soften. In quantum field theory, fields do not merely exist and then act. Their existence is their activity. A field at rest is not inactive. It is simply in its lowest allowed state. Light appears when that state changes, when the field moves from minimal expression into articulation. This means that motion is not something added to being. Motion is one of the ways being expresses itself. This reframes the idea of energy in a subtle way. Energy is not a substance carried by photons. It is a measure of how the field is configured. A higher energy photon corresponds to a more rapidly varying field state. Energy is pattern intensity, not payload. Fascination. Energy as shape rather than stuff. This also explains why light cannot be peeled open to reveal internal components. There is no inside. There is only configuration. A photon does not contain energy the way a container holds water. The energy is the photon. The excitation and the energy are the same description viewed from different angles. Quantum field theory becomes especially elegant here. The Hamiltonian of the electromagnetic field, the operator that encodes energy, acts directly on field states. When it acts on a state with one excitation, that excitation has a precise energy. There's no intermediate layer where the energy resides separately from the field. This directness is one of the quiet strengths of the theory. It wastes nothing. Every concept earns its place. Fascination. Economy without reduction. Another subtlety emerges when considering how light relates to time. Because photons are massless, their existence is inseparable from motion. There is no rest frame for light, no moment where it simply is without propagating. To exist as light is to move. Not metaphorically, but structurally. This means light is always in transition. It never lingers, it is never static. Even trapped light, such as in a cavity, is still propagating, reflecting, oscillating. Its stillness is an illusion created by symmetry and boundary conditions. Fascination. Stillness revealed as balanced motion. Quantum field theory handles this naturally because fields are inherently dynamical. They are defined not by positions, but by evolution. Light fits seamlessly into this description. It is not a static entity that later moves. It is motion given form. This sheds new light on the idea of propagation. When light travels, nothing migrates from point A to point B. Instead, the field at A influences the field nearby, which influences the field slightly farther away, and so on. The pattern advances, but no individual entity makes the journey. This is why light can be delayed, slowed, or reshaped without contradiction. The field's evolution can be modified by environment without ever needing to shepherd particles along a path. Fascination. Travel without travelers. This perspective also makes it easier to understand why light does not violate causality even when its quantum behavior feels non-local. The field evolves locally. Entanglement does not transmit influence faster than light because influence is not what is shared. What is shared is correlation in the field's state. Local evolution remains intact. Light enforces the ultimate speed limit not by rule, but by structure. The field equations simply do not allow faster propagation. Nothing is forbidden. It is just impossible. Quantum field theory thus places light in a role that is almost architectural. It defines the edges of influence, the shape of causality, the slope of time itself. Light is not just something that happens within the universe. It helps define what can happen at all. Fascination. Constraint as foundation. This brings us gently to the edge of the next part, where light begins to illuminate not just fields, but the very idea of space-time itself, where quantum field theory and relativity begin to interlace more tightly, and light reveals why space and time are not passive arenas, but active participants in the unfolding of reality. And so the electromagnetic field continues, everywhere, quietly holding its readiness, quietly permitting motion, quietly allowing energy to take shape, while light appears whenever that readiness is nudged into expression, not as an object sent forth, not as a wave in a medium, but as the universe momentarily expressing how change moves when nothing material needs to move at all. A living demonstration that reality, at its deepest level, is not built from things, but from patterns that are allowed to flow,